Okay, the next thing that we're going to look at here is the remainder theorem. Okay, and ultimately what it boils down to is if we have a polynomial that's divided by x minus k, okay, the remainder is f of k. So I want you to notice two things about this theorem before we start looking at it. We can have a polynomial, it could be any polynomial, it could be whatever degree we want it to be. Okay. But when we divide it by x minus k, I want you to notice the key thing here is that we're dividing it by something linear. Okay, we're dividing it by x minus k, or x minus 5, x plus 3, x minus 24. Okay, it's got to be a linear divisor, okay, in order for this theorem to help us. And the other thing that it has to be is it has to be in the form of x minus k. It can't be 2x minus 5, let's say, because that's not in the form x minus k, is it? Okay, so this is not going to work. It's got to be in the form x minus k. So if you have that situation where you're dividing a polynomial by x minus k, okay, you can find the remainder without actually doing the division. Okay, and remember, what would we want to look for here to find the remainder? What would do us good if the remainder was what? Yeah, think about what would happen if the remainder were 0. That would tell us that this is a what? It's a factor. Okay, which is really what we're after here. We want to see if this is a factor or not. Okay, so what it boils down to is we need to figure out what that is, because that is the remainder. Okay, so in practice, this is what that's going to look like. We're going to be given some polynomial, like this one. Okay, and the question is, find the remainder when we divide this by x plus 3. Now, of course, we could do what we did in the previous problems, and we could take this and we could do the long division, and we could figure out if the remainder is 0 or not, or whatever it is. Okay, but what the remainder theorem tells us is that we can find the remainder by just putting the 0, the would-be 0, if you will, it's not necessarily a 0, into the equation and doing the math. Okay, and again, how did I get negative 3? Because if x plus 3 is the factor, then x equals negative 3 would be the possible 0. And again, it's only the 0 if it actually makes the answer 0 here. Okay, but ultimately it's not. It's the would-be 0, but really, no matter whether it's a 0 or not, it's the remainder. If we plug that in and we get an answer, it could be a 0, could be something else. The bottom line is it's the remainder. So when we do the math on that, we're going to get 9 here times 2, that's 18, plus 3, plus 12. So in this particular case, we get 33. So again, the answer to the question is 33. That's the remainder when we divide this by this. Okay, and it's not 0, so that means that that's not a factor, which means that this is not a 0. Fair enough. Okay, but what does that do for us? If all we're trying to find is the remainder, it saved us a bunch of work, didn't it? Okay, we didn't have to actually do the division. Okay, if we did the division, we'd wind up with 33 as the remainder, and we could get it that way too. But if we want to use the remainder theorem instead, okay, all we got to do is take the k, if you will, because remember this is of the form x minus k. So we'll take the k and plug it into the equation. Okay. And if you have a graphing calculator, this would be really easy, because you could just put that in y equals, and you could do your table and put negative 3 in there, and you could get the remainder immediately without even doing any math. True? All right. Now, the other theorem in here that we're going to look at is what we call the factor theorem, and we've already alluded to the fact that this is true. Okay, and this is kind of summarizes what we've been talking about, that if we have a polynomial function, again, any polynomial, okay, and we know that it has a factor x minus k, okay, then f of k is equal to 0. So in other words, x equals x minus k is a factor, then k is a 0. And what's nice about the if and only if right here is that both of these things are true whether we read it left to right or right to left. So if x minus k is a factor, then k is a 0. Okay, or if we know that k is a 0, then x minus k is a factor. Okay, in fact, we used that today earlier because weren't we given 3 zeros? And what did we do with those 3 zeros? We wrote them as factors, didn't we? To get back to the polynomial we started with. Okay, we actually used this theorem even though we didn't have it in theorem form at the time. Okay. All right. Questions so far? All right, in your book, I want you to look at page 224. And on page 224, you have problem number 20 I want to look at together. We have, they tell us that x minus 3 and x cubed minus x squared minus x minus 15 is our polynomial. And the question here, it says use the factor theorem to determine whether the first polynomial is a factor of the second polynomial. Okay. So this is number 20. Page 224. All right. Now, before we actually do that, before we use the factor theorem, because again, okay, it's a factor, and this is really kind of just a special version of the remainder theorem that we just did. Okay, if we know that this is a factor, oops, excuse me, then if we put k into the equation, we would get 0. True? So that means that for our work on this, this is what we would show. We would say that, okay, k is equal to 3 then if I have x minus 3, because remember the general form is x minus k. So that means k is equal to 3. You might want to write that down. Okay, and if we were to put 3 in here, and do the math, we'd get 3 cubed, that's 27, minus 9, minus 3, minus 15. And if we go left to right and subtract, we'd get 27 minus 9, that is 18. 18 minus 3 is 15, and 15 minus 15 is equal to what? 0. So the answer to the question then is what? Is this a factor of this? Yes. Okay. And we can find out by using the factor theorem. Now, is there another way we could have figured that out, that that was a factor? At the beginning today, we learned how to divide these two polynomials, true? So if we did that long division process and found that the remainder is 0, we would have a factor, wouldn't we? Okay. Now, I'm going to introduce you to another type of division, as I mentioned earlier. Okay. And this type of division is going to be what we'll probably use primarily from here on out. Okay, because for the most part, really the only reason that we would divide polynomials is to figure out whether one was a factor of another or not. Okay? And most of the time we're trying to figure out whether a linear factor is a factor of something that's not linear. Fair enough? All right. So the division that we're going to look at now is what we call synthetic division. And you're going to like this because it's easier to do than the other one. Okay? So with synthetic division, the general rule is going to be is we're going to take our whatever our k value is here, and keep in mind we have to have something of the form x minus k. If it's not x minus k, then this synthetic division does not work. Okay, so on the first two problems when we were dividing by a quadratic equation, that's not going to work. Okay, it's got to be a linear possible factor. Okay, and it's got to be of the form x minus k. We can't have a number in front. It's got to be x, not 2x or 5x. It's got to be x minus k. So if I were to do synthetic division with this, what I'd do is I'd put my k in a box. Okay. And then I would take my coefficients on what I'm going to divide into. Okay, and I'm going to put them next to each other up here. Keep in mind that if there are missing terms, okay, there has to be zeros in those places. If you don't put zeros in those places, this is also not going to work. Fair enough? All right, and then what I'm going to do is I'm going to leave a space, and I'm going to put a bar down there, and this is how I'm going to set up every synthetic division problem that I do from here on out. Okay, so k goes in the box. I'm going to put the coefficients on this line, and I'm going to leave a blank line here, and ultimately I'm going to do some work here, and I'm going to get an answer in just a minute. But here's what the process is. Okay, and it's going to just take some practice, just to follow the rules and just do exactly what I do every time. We're going to take the leading coefficient, and we're going to put it right straight down here. Okay, so the leading coefficient does that, goes right down there at the beginning. And then what we're going to do is we're going to take the k, and we're going to multiply by this number, and we're going to put the result right here. Okay. So we're going to go 3 times 1, and put the result right here. And then what we're going to do is we're going to add that column together, and we're going to get an answer, which is 2. Okay. right? And then we're going to do 3 times 2, and we're going to put that result right here on the next line. And then we're going to add again. And then we're going to go 3 times 5 and put that result here, and then we're going to add again. Now, once we do that and we get done, then we're going to put a little bar right here, because what that bar does, it separates for us Q of x and R of x. And we know R stands for the what? The remainder. And what is the remainder as we expected? It's 0. That's good, right? And ultimately, by doing this, what have we found? That if we were to have divided these with the long division process, we would have gotten a 0 remainder, which tells us that 3 is a 0, and that x minus 3 is a factor. True? Okay, but what it does for us even more importantly is it gives us Q of x. Okay. So at this point, remember, what I ultimately want to be able to do is I want to be able to factor this cubic. True? So I'm almost there. I already know that x minus 3 is a factor. I also know that x squared plus 2x plus 5 is a factor also. Because again, these are the coefficients of Q of x. Okay, this is the quotient part. And as we said before, if I divide and I get a quotient and a 0 remainder, the quotient part and the divisor are factors. Okay, so what have I done with that cubic? I've broken it down into a linear and a quadratic. Okay, and remember, ultimately, what I'm going to want to do is completely factor this, okay, or set it equal to 0 and solve it. Okay, I'm well on my way. I already know what one of the zeros is. It's 3. And the other 2 zeros are going to come from this. Okay, and this is quadratic. And what do we know how to do? We know how to solve any quadratic equation, don't we? So if we can break that cubic down into a linear and a quadratic like we just did, okay, we're just about done then, aren't we? Okay, if I were to set this equal to 0 and solve it, I could do that easily. I already know the answer to this one. I would either use the quadratic formula or factoring to solve this one, and I could find all 3 zeros then, couldn't I? Okay. So think about what's going to happen if I were to give you one that was quartic. And I gave you one of these and I said, see if it's a factor or not, and it was. Okay. When we get done, what's the Q going to be like? If I did a quartic and a linear, the Q is going to have degree what? 3. So if we had this in a degree 3, we still wouldn't be home free, would we? Okay, because again, we'd be in a cubic. But what could we do with the remaining cubic? If we knew another factor, we could divide again, couldn't we? And if we had a linear, and quadratic, then we'd be home free. True? And that's really what the process is. We're taking a higher degree function than 2, cubic, quartic, could be 5th, 6th, 10th, whatever it is. If we can find one factor, then we can break that down into something smaller. If we can find 2 factors, then we could break it down into something even smaller yet. Okay, and so that's the general process, is to break that down into smaller degreed functions. Because once we get into quadratic, like I said, we're home free. We can solve that with either quadratic formula or factoring. Now, knowing that, and I'm going to give you a little preview of what we're going to do down the road here a little bit. Okay, what if I wasn't given this? If all I said is factor that. Okay, how would I know what might be a factor of this? What's that? It might have something to do with 15. That's a good guess. Okay, and that is actually a really good guess. Okay, but what other way do we already know that we could maybe figure out what a factor might be here? What do we all have in our hand right now or sitting on our desk? If you have a calculator, couldn't you look at the graph of this and see what the x-intercepts are? If you graph this, it would look like it goes through 3, so wouldn't 3 be what you try to divide it by? Sure. Okay. So we have most of the processes down a little bit. We're going to learn quite a bit of other stuff here as we go throughout the rest of Chapter 2 here, but that's really the process. Okay. If we can find one factor, or even 2 factors, that'd be even better. Okay, then we can break this down into smaller parts, and hence we can get a factorization that is either linear or quadratic, and once we get to that point, then we can find everything that we need.